Hello, everyone. My name is Roland Szakacs. I'm a PhD student of Celine Peru and Martin Swan at the European Southern Observatory. And today I would like to talk about a paper that I recently submitted and which is currently under the review process. It's called MUSE-ALMA Halos 6, Coupling Atomic, Ionized, and Molecular Gas Kinematics of Galaxies. So first, what is MUSE-ALMA Halos itself? It is a multi-wavelength study of a large H1 absorber sample. So we study absorbers and galaxies associated with those absorbers, and we want to find out how they are connected. There's a number of previous publications from this already, so feel free to check those out. Then in this paper, MUSE-ALMA Halos 6, we focus on studying the molecular gas content of these galaxies associated with those absorbers, and we use a pilot sample of 5 quasar fields, which have follow-up observations by ALMA. So in these 5 fields, we have 6 absorbers and 9 associated galaxies, and we detect roughly half of them with ALMA. So this paper heavily focuses on one of these detected galaxies called Q2131G1. Here you can see the various properties this galaxy has, and also a flux contour map. I'm not going to go into detail about these properties here, but this is just to give you an idea of what kind of galaxy this is. One thing I would like to discuss in more detail, though, is the kinematics of this galaxy, specifically of the molecular and ionized gas phase. On the left-hand side, you can see the observed velocity maps of both of these phases. And we use a 3D forward modeling approach by Galpac 3D to model the kinematics of both of these gas phases within the galaxy. We find that both of the phases are closely correlated. So we have closely correlated velocity fields. We have roughly the same maximum rotational velocity of 200 kilometers per second for both the molecular and ionized gas phase. And we also find that they're aligned well directionally. So they have similar inclinations and similar position angles. Using kinematic modeling, we can also study the gas absorber connection. We extrapolate the modeled velocity maps toward the line of sight of the quasar, which is indicated by the magenta and brown ellipses on the maps, to find out the expected rotational velocity of the gas at that position. In the middle, one can see various spectra. The top 2 panels display the molecular and neutral absorption features found in the absorber, while the bottom 3 display the spectra of the ionized and molecular gas found in the galaxy. The extrapolated velocities of the galaxy are displayed as the magenta bar for the molecular gas and the brown bar for the ionized gas. As one can see in the absorption spectra, we find 2-component absorption features, with the weaker component being blue shifted, while the stronger component is redshifted compared to the systemic redshift of the galaxy. Based on the velocities, the weaker absorption component is consistent with being part of the extended rotating disk of the galaxy. We can also extrapolate the metallicity of the galaxy and find that the extrapolated metallicity at the position of the quasar sightline is also consistent with the absorber metallicity. The velocities of the stronger absorption component are consistent with being gas falling onto the galaxy. The metallicity of the absorber is also consistent with being infalling gas. But finding H2 in this absorber, of course, poses the question if and how a molecular gas phase can exist in infalling gas. So this already brings me to the conclusions. So MUSE-ALMA Halos is a multi-wavelength study of a large H1 absorber sample. The specific galaxy that I just talked about has a strongly coupled ionized and molecular gas phase in a rotating disk. The 2-component absorption features are consistent with in part an extended rotating disk of the galaxy and in part falling onto the galaxy. And there's a lot of more further discussion in the paper itself, where we discuss the morphology of the galaxy, the dark matter fraction, also some specifics of H1 selected galaxies. Like we find, for example, that there's some indication that H1 selected galaxies might trace objects that have large molecular gas reservoirs at a given star formation rate. And we also provide limits for non-detections. So if you have any further questions or anything else, feel free to contact me anytime. Thank you very much.